Ok. On m'entend bien?
Bonjour, je suis un membre du jury, je parle pas très fort, mais... Bonjour.
En fait, faut pas que tu regardes YouTube depuis ton faut le regarder depuis ton téléphone, je pense que ça fait une Tu veux qu'on se soit où? Je pense que ça fait une
Tu es en contact avec elle? Ok. Et du coup, enfin, lui, il dit plus tard, et je dis qu'il faut que ce soit un peu plus de jours. Ah, très bien.
So, okay, so good afternoon, everybody, and Daniela, members of the jury. Can we? So the two referees are online and they can hear us well. Can they give a sign? Yes, yes. Perfect. Okay. So Daniela, please, we are happy to listen to you.
Am I
yes, please. It would be much better.
Okay. C'est bon? Okay, so thank you all of you for being here today. I am happy to give this talk to you. So this is my PhD defense. I will present to you the work that I have been doing here during my 3 years of thesis at the Institut d'Astrophysique Spatiale. I studied mainly the largest scales of the universe and more particularly the cosmic filaments. And this work was done under the supervision of Mathieu Longuer and Nabil Aghanim here. And my thesis is entitled Characterizing Cosmic Filaments and Their Surroundings in Large-Scale Hydrodynamical Simulations. Okay. So in astrophysics, we use satellites and telescopes to map the sky. And for example, we can see the positions of galaxies and do a map of the sky as we see here. So in this figure, this is an actual observation. Each point here represents the position of a galaxy, and we observers are here. And the galaxies that are located near the center are galaxies that are close from us, while far from the center, we have galaxies that are very distant from us in space and time. So this figure shows the large-scale distribution of the galaxies in the universe. And what is striking here is that at these large scales, the distribution of galaxies is not uniform, because we see zones of the sky that have very few or even none, any galaxy, and others that are more denser and where the galaxies are assembled in these zones. And all these structures are connected, and the galaxies are distributed, forming filamentary structures. And all of this is called the cosmic web. So the cosmic web has not only been seen in observations, but numerical simulations such as Illustris TNG and others also managed to reproduce this web. And for example, here we see a slice of a simulation box in which each point is a galaxy. And we can also see the large-scale distribution of the cosmic web. And what we can see is that we have 4 different main structures. First, we have the voids. So matter departs from the voids and goes to the walls of the cosmic web. Here, since it's a 2D slice, it's hard to see the walls, but we can better see them here in the 3D representation. The intersection of walls define what we call the filaments, and matter flows from the filaments to go to the nodes, the densest structures of the cosmic web. All of this is ruled mainly by gravity. And in fact, gravity is what is the main constituent of the cosmic web. As we can see it here, gravity actually assembles and, dark matter assembles and forms the gravitational potential wells on which matter is attracted to. And galaxies actually trace the position of the dark matter gravitational potential wells. But we say that galaxies are biased tracers of the matter distribution because we find them only in the densest regions where we have the most of dark matter. Of course, the cosmic web is also composed by gas and galaxies are what we call the ordinary matter. We call them in astrophysics the baryonic matter. And baryons follow the dark matter skeleton. And they, unlike dark matter, they can be heated and they can be cooled. And so they can emit and they are visible. So these are the matter components of the universe. And what is interesting, just wanted to tell you that these matter components represent only roughly 30% of the total budget of the universe. And most particularly, baryons are roughly 5% of our universe. And the dominant part is dark energy. So this is something that is responsible for the accelerated expansion of the universe that we measure today. But in my thesis, actually, I focus only on the matter components. And I study the distribution of matter around the cosmic filaments. So several studies based on numerical simulations have quantified the volume fraction occupied by the 4 different structures of the cosmic web. And for example, here in this plot, we can see that voids occupy the most of the volume of the universe, and filaments only roughly 5%. However, filaments host half of the matter of the universe, and this is the case for the dark matter and gas components, and even a larger fraction of mass of stellar mass is hosted by cosmic filaments. So the study of matter in the larger scales is really tied toward different cosmic structures that I showed before. And for example, towards the highest density part, we see the distribution of the nodes. Towards in yellow here, here we see the distribution of the voids. And what is striking here is that the filaments, so in blue, occupy a huge range of densities, spanning almost 5 orders of magnitude. So this is very intriguing because it means that we have filaments that are underdense with respect to the mean density of the universe, and others that are overdense. Imagine, for example, that you observe a filament that has a density similar to that to the nodes. Most probably this filament will not have the same physical properties than a filament that has density similar to voids. So this is something I wanted to study during my thesis. Given the observed diversity of cosmic filaments, I wondered, are they all the same type of structure? Are the filaments of different densities, of different properties, are they all comparable? Are we talking about the same type of structure? And since filaments contain half of the matter of the universe, what are the properties of matter around them? And what could observations tell us? So during my thesis, I tried to answer to those questions by using numerical simulations. So this is how I proceeded, basically. I used hydro-dynamical simulations, and I applied a filament detection technique that is called disperse. And then I built filament catalogs, and with filaments in hand, I could analyze the galaxy radial distribution and also the dark matter and gas distribution. And I also was interested in the properties, in the physical properties of gas and galaxies around the cosmic filaments. And my aim was to build a more comprehensive picture of matter around the cosmic filaments today. So, first, are all the filaments the same type of structure? So what I did was to analyze the way galaxies distribute around the cosmic filaments, and I explored the variations of the galaxy distribution with some properties, basically the length of the filament. And this showed that actually we can separate filaments into different populations. So this is, and then with the filament populations that I detected, I wondered if they were signatures of the different populations on the properties of matter. But before presenting the results, I will present the tools that I used. So hydrodynamical simulations, what are they? So imagine you have a box, a simulation box, and inside you put dark matter and gas particles. You put also the laws of physics that we know, so gravity, the laws of fluid mechanics, and also physical models or recipes that are here to help us dealing with all these smaller scale phenomena, such as the feedback from the feedback effects or the star formation. And so with this box, we make evolving time, and we see the emergence of the cosmic web until z equals 0. That means today. So in my thesis, I use 5 different simulations with different characteristics. So in this figure here, we see the box size length. So it's basically the volume of the simulation and the resolution of the simulation. And for example, I used the magneticum simulation. That is the largest box that I used, but also has the lowest dark matter resolution in comparison to the other simulations. The Illustris 2 has one of the best simulations, resolutions, but has a volume that was limited in comparison to the other volumes. So the best choice I found was the TNG 301 simulations. So this is the best compromise between resolution and volume. So this is the simulation that I use as a reference during all my studies. We can have different outputs thanks to numerical simulations. For example, the dark matter density field, the gas density field, gas velocities, and halos. Halos are actually found by post-processing the dark matter and gas distribution thanks to dedicated algorithms. And the halos have a broad distribution of mass. And I selected the halos according to the stellar mass they contain to build simulated galaxy catalogs, such as this one here. And the simulated galaxy catalogs are at the basis of the cosmic filaments that I will detect. So how do I detect the filaments? From the distribution of galaxies, the dispersed algorithm, so this is a publicly available algorithm that I apply to the different simulations. So dispersed computes the 3D continuous density field, and then it extracts the topological information, meaning the critical points of the field, such as the maximum density critical points, the saddle, and the local minimum, as we can see it in this analogy with a mountain. And then the filaments are the sets of segments that connect maximum density critical points to the saddles, as we can see here in this illustration of a natural skeleton of a cosmic skeleton and not a mountain, where the maximum density critical points are in the densest zones of in the over-dense regions of the web. So I had 5 different simulations, so 5 different catalogs, and each one had a different number and a different length of filaments. And these 2 properties dependent on basically 2 things. First, the size of the simulation box. So of course, boxes that have larger volumes have more filaments and also longer filaments than boxes with smaller volumes. And the second parameter was the density of galaxies. So this is basically the level of refinement, the detail of the underlying density field. For example, here for a same volume of the simulation, the TNGA 301 has more filaments than the medium resolution counterpart, and this is because of the higher density of galaxies, so higher resolution basically of the density field. Despite the fact that these are 5 different simulations, the filament length distribution had similar properties, as we can see it here. All of them peaked at around 5 megaparsec. We have more short than long filaments. So these simply tell us the multi-scale character of the filamentary network. And they also showed an exponential tail, which is in agreement with other simulations and other studies also in observations. So it's important to test the robustness of the skeleton before analyzing how the matter and how the properties of matter around the filaments detected. So for this, I just need to tell you that actually this purse has 2 important parameters. These are the smoothing of the density field. So this is basically one can choose how to mitigate the effect of shot noise arising from a discrete distribution of points, such as the galaxies. So we mitigate this by smoothing the density field before applying the rest of the disperse algorithm. And in my studies, I set the smoothing of the density field to one cycle, because increasing this the number of cycles of the density field smooths too much and erases the topology. So we cannot find filaments that actually describe the topology. The second parameter is the persistence threshold, and this parameter basically helps us to find the actual filaments with respect to the filaments that are in the noise, that arise from the noise. And to do so, I tested different persistence thresholds, and of course, a reliable skeleton is one that where the most dense densest structures of the cosmic web are detected by, for example, the maximum density critical points. So in this plot, we can see here the different halos of the simulation, and in yellow we see the clusters of galaxies, so the more massive halos, and we want the clusters to host the maximum density critical points. And the 3 sigma skeleton was the one that traced the best these massive structures, because when we increase the number of sigma of the persistence threshold, we see that the matching is not good. So of course, I wanted to check that not only the position of the maximum density critical points was well traced, but also the way the matter is distributed around these points. So I compared the masses of the CP max and the halos, and I found that the CP max had similar mass distribution as the halos, as the clusters and the groups. And I also compared the distribution of matter around the maximum density critical points and the different halos, thanks to dark matter density profiles. And I found that similar shapes and amplitudes of the matter distribution with the most massive structures. So the best choice of parameters in this simulation is a smoothing of 1 cycle and a persistent threshold of 3 sigma. And this gave me a reliable skeleton. So now that I have a skeleton that is robust, I want to start like to ask the question: where are they? Are all the filaments the same type of structures? So in order to do that, to explore this question, I studied how the galaxies, so the tracers of the density field, are distributed around the filaments. And to explore the diversity of the different filamentary structures, I focused on the length. But first, let us ask the question, what can the radial distribution of galaxies tell us about the cosmic filaments? So with the filament catalogs that I had, I built radial density profiles, basically by counting the number of galaxies in concentric hollow cylinders around the axis of the filament, and I divided this number by the corresponding volume. And as I wanted to have a signal that only comes from filaments, I removed from my analysis the contribution from nodes. So the most massive structure that may contaminate the signal of filaments. I built average profiles of the filaments. So this is I obtained this average profile of the different for the 5 different simulations. And first, we can see that when we are far away from the filament, as expected, the galaxy density is similar, is compatible to that of the background. And as we approach the core to the spine of the filament, we increase the number of the galaxy density, and we reach the highest densities in the most inner part of the filament. 4 simulations have very similar profiles, but we have one simulation, namely the illustrious simulation, that deviates at the core. And actually, I tested that this was due to the feedback model of this simulation that is too strong and that ejects the matter away from the most most dense regions of the cosmic web, yielding on a deviation of the profile at the core. But for simulations that actually have feedback models and bionic models that are calibrated on observations, the similarity between the profiles shows us that the essential and dominant driver of the distribution of galaxies is gravity. So I explored the variations of galaxy density with a property of filaments, that is the length. And to do so, I built 8 different bins of length of the filaments, and I repeated the previous study on each one of the bins to build the density profile of each of the bin. And we can see here that the shortest filaments have always values of the density that are above the average of all the filaments, while the longest filaments are below the average. I wanted to quantify the differences between filaments of different lengths, and I computed the deviations of each bin with respect to the average value. And by fixing a threshold at 2 sigma, I could identify 2 extreme populations that are the short filaments, so shorter than 9 megaparsec, and the long filaments, which are longer than 20 megaparsec. And I performed a Kolmogorov-Smirnov test, so statistical test, that showed me that actually the 2 populations of filaments are different. So here you can see the average profile of short and long filaments for each one of the simulations. And you can see that always at all radial scales, short filaments have higher density values than the long ones. And if we fix, for example, if we look at a fixed density, we can define a characteristic radius of that shows us that actually the short filaments are puffier and the long filaments are thin. So I wanted to have a more quantitative measurement of the differences between these 2 populations of filaments, so the short and the long. And to do so, I fitted the average profiles of each population with 5 different models inspired from the cluster literature. And what you can see here is the result of such fits. So in the y-axis, we have the reduced chi-square. That's basically the quality of the fit. And we can see that the short filaments and the long filaments are better fitted when they are taken separately than all mixed together. If we see the resulting parameters, for example, here for a single power law, we clearly see that the contours of the describing the different filaments are different and are disjoint. So these two populations are fitted by different parameters, showing a quantitative confirmation of the difference. I wanted further to further explore these two populations by actually showing, or I wanted to know if there was a physical reality of short and long filaments. Can we physically identify these two populations in the cosmic web? So to do so, I basically integrated the profiles and I found the excess of density with respect to the background. And this showed that the statistically short filaments are denser than long filaments. And I also computed the mass of the node connected to the filament. And this showed me that short filaments are connected in a statistical way to more massive objects than long filaments. So actually, these two populations trace different environments in the cosmic web. As we can see in these panels, the short filaments trace overdense regions, for example, at the vicinity of the most densest structures that are the clusters of galaxies here in orange, and the long filaments trace less dense regions. So let's go back to the first questions. Given the observed diversity of cosmic filaments, are they all the same type of structure? So I studied the galaxy evolution of cosmic filaments, and by exploring the variation of I studied the galaxy distribution of cosmic filaments, and by analyzing the variation with length, I identified two extreme populations that trace different environments of the cosmic web. So short filaments are short and puffy, they are denser, they are tracers of overdense regions, and they may correspond to the bridges of matter between the overdense structures such as clusters. On the other side, long filaments are long and thin, they are less dense, they are tracers of less dense regions of the cosmic web, and they may correspond to the cosmic filaments that shape the largest scales of the cosmic web. So we have two populations of filaments determined by their length. Can we see them? Can we see these two populations in the properties of matter? What are the imprints of these two populations on the matter on the properties of matter? So let us start first by focusing on the properties of gas. So in the cosmic web, not all gas is the same, because the accretion, the ejection, the heating, and the cooling that is to which gas is subject pushes gas into different physical states of phases that coexist in the larger scales of the universe. And we can actually distinguish these phases by using a phase space diagram such as this one, that is just the relation between density and temperature of gas. And for example, we have hot gas, that is the gas that is located in the where we have the most of the matter in the universe, such as for example, the clusters of galaxies. We have wind gas, that is gas that is diffused and is heated by as it's accreted towards the cosmic structures. We have diffuse IgM, that is the gas that is located in the less dense regions of the cosmic web. And on smaller scales, we have the WCGM and the halo gas, that is denser and colder gas that is located nearby or inside the galaxies. So how are these phases shaped by short and long filaments? So I separated, of course, these two populations of filaments, and I removed the gas in the nodes. And also I removed the gas located in the most massive halos of the cosmic web, because we know that filaments might contain halos, and I wanted to remove the contribution of these collapsed structures in the signal of really the interfilament gas. So I built the profiles of mass fraction for each gas phase, that is basically the density of a given phase with respect to the total gas density. So what we see here, so far away from the spine of the filament, most of the gas is in a diffuse and diffuse IgM and WIM phase. And as we approach the core, as we approach the filament, we have a decrease of the fraction of diffuse IgM accompanied by an increase of gas in the WIM. And this shows that the diffuse IgM is being accreted towards the filament and heated, and thus converted into WIM gas. WIM reaches the maximum values at roughly 1 megaparsec from the spine, and then the fraction of WIM decreases because we have the emergence of new hotter and denser phases, such as hot gas or halo gas. And what we can see here is that the trends are the same for short and long filaments, but the exact values differ. For example, long filaments have larger contributions of diffuse IgM. But we need to take into account that the frontiers between these two, between the different phases must not be considered as sharp boundaries. They are only guiding references. And in order to better understand the cores of the filaments, I perform a more refined study at the cell level. So I basically selected the gas that was located in the core of filaments, and I plotted the phase space of this gas. And what we can see here is that the contours of short and long filaments are different. For example, long filaments are shifted towards the cooler values, and short filaments possess a contribution of hotter gas. And here in green and red, you can see the contours of halos and of the nodes of the cosmic web, the maximum density critical points. So this showed me that the short and long filaments have different gas content. And we can link that with, of course, the different environments, with the overdense and underdense environments of short and long filaments. So how do these differences translate in the gas observables, such as the temperature and the pressure? So I computed radial temperature profiles that we can see here. And again, we see yet another differences between short and long filaments, because short filaments are roughly 3 times hotter than the long ones. Also, all the filaments presented a isothermal core. So this is a property that has also been seen in other studies of numerical simulations. Regarding the pressure, the same trends were found of the differences between short and long, because the pressure of short filaments is, I found it to be also roughly 3 times higher than the pressure of long filaments. And I wanted to compare this with what we know of clusters of galaxies. So these are structures that are easily seen, so more studied than cosmic filaments. And so what you can see here is the pressure distribution of the 2 different populations. So first we can see that it's not the same distribution. And here you can see the pressure distribution of the clusters. So I found that pressure in cores of filaments is roughly 1,000 times lower than the pressure in cores of clusters. What is nice about pressure is that it's directly related with an observable that is called the Sunyaev-Zeldovich effect. So we can observe a gas thanks to this effect that is basically the interaction of high temperature electrons, for example, located in filaments, with photons of the CNV. So from the pressure profiles that I just showed you, I estimated the minimum and maximum Y signal of, so Y signal is the signal of the Sunyaev-Zeldovich effect. I estimated this for short and long filaments by taking two extreme filament orientations. So first, the minimum of the signal was given where the filament is completely perpendicular to the line of sight. So these are the minimum limits, and the maximum of signal is given where the filament is completely parallel to the line of sight. So the shaded regions show the maximum and the minimum and the upper bounds. And I distinguished two cases. One, when I considered only gas not in halos. So this is what I call the interfilament gas in dark colors for short and long. And the second one is when I included the contribution of halos. So halos, as they contain hotter gas than filaments, they increase the Y signal, and the increase is roughly 3 times, as you can see it here. And I wanted to use this to interpret observations. So in gray here, you see the mean Y profile from Planck data. And so this is a profile that was found by Tanimura et al. 2020, and they basically stacked the Y map around long filaments found using the disperse on the SDSS. And we can see that this Y profile is compatible with the regime, with the estimation in which halos are excluded, meaning that the observed Y signal is of this study is mostly due to interfilament gas. So the comparison between observation and simulation is important because this allows us to confirm or to better interpret, to better understand results from observation. So in summary, what are the properties of gas around filaments? At large scales, mostly all of the gas is in a diffuse IgM phase and WIM. As we approach the core, we have the accretion of gas towards the filament, and this diffuse gas is converted into WIM. WIM reaches its dominant phase at roughly 1 megaparsec, and the cores of filaments also are dominated by WIM gas, but other hotter and denser phases also live there, and cores of filaments are isothermal. And we have the observation of two populations, not only in the distribution of galaxies, but also in the gas properties. As we can complete this table that I showed you before by saying that short filaments are hotter and have higher pressure values than long filaments. So, from the study of gas that I just showed you, we have 3 regimes that naturally emerge. So these are the largest scales, the outskirts, and the cores of filaments. And I wanted to know if gravity explained the emergence of these three regimes, and what are the driving processes of matter in each one of these regimes. So the ideal observable to study to answer to this question is the baryon fraction of filaments. So why the baryon fraction? It's because this observable allows us to study the relative distribution of baryons, so gas and stars, with respect to dark matter. So what we can see here is the baryon fraction profile of short and long filaments, and this horizontal line represents the cosmic value as found by the Planck collaboration. So here again, we have three different regimes that emerge, and they are defined by the intersection of the profile with the cosmic value. So the three regimes are first, where the filament profile is compatible with, the baryon fraction of profile of filaments is compatible with the cosmic value, and that means that in this regime, matter simply falls into the filament potential wells. Then we have an excess of baryons with respect to the cosmic fraction, and then a baryon depletion. So I will now explain to you regimes 1 and 2 that are basically the regimes that we can say that are inside the filaments, as this Rx radius might be characterizing the radial extension of baryons in filaments. So first, the baryon depletion at the cores. So in order to have a depletion of baryons, we need a mechanism strong enough to be able to eject gas away from the cores. So I investigated whether the feedback effects by AGNs were strong enough to expel this gas from the filament cores. So to do so, I computed the gravitational potential well of filament, which is presented here. So again, we see a difference between short and long filaments because the gravitational potential well of short filaments is deeper than the one of long filaments. And I also computed the mean kinetic energy per unit of gas mass injected into the medium by the AGNs. So by computing the ratio between these two quantities, I am quantifying the competition between the pulling of gas towards the gravitational potential well and the pushing of gas led by the feedback of by the jets of the AGN. So again, we can see differences between short and long filaments that reflects the difference between the potential well, and this can be understood in analogy with the clusters of galaxies, because we know that the most massive clusters of galaxies are barely affected by AGNs, by the effects of AGN. But we found that there's both short and long filaments have a regime in which the ratio is higher than 1, meaning that these feedback effects can be powerful enough to potentially deplete the filament cores. But of course, not all the energy injected into the medium by these astrophysical processes is transferred into the gas, because we need to take into account we need to take into account, for example, the jet orientation of the AGNs, the geometry, the coupling with the gas. Let us now focus on this at the intermediate scales, the outskirts of filaments, where we see the baryon excess with respect to the cosmic fraction. And in order to interpret this, I again disentangled the contributions of the different gas phases, as we can see here. So this is the gas fraction of each gas phase, and it's evident here that the bump, the excess, is due to the WIM gas. So this reflects, this is in very good agreement with the results that we just saw before, where I present to you the gas properties. So this just means that the WIM gas is assembled at the outskirts of filaments due to the gravitational accretion of diffuse gas towards the core. So we have seen that we have different populations, and that the gas properties in each population is not the same. Short filaments are hotter, they have higher pressures, they are overdense, and long filaments are colder, lower pressure values. How is this translated in the properties of galaxies? And most particularly, we know that galaxies need to be supplied by cold gas in order to fuel the star formation. And I want to further investigate how does the different environments of short and long filaments affect the star formation activity of the galaxies living in each one of these extreme populations. So this is a first attempt, a first exploration on the properties of galaxies in the different filament populations. And in this plot, you can see the mean specific star formation, so the SSFR of galaxies. So first, we see that the star formation activity of galaxies decreases when we approach the cores of filaments. So this is in agreement with studies in observations. And what I showed here is that this decrease actually starts at the Rx of 7 megaparsec, that is the radial extent of gas defined as by the previous study of the baryon fraction profiles. So maybe this decrease might be due to, for example, the disconnection from the cold supply of gas, or the thermal evaporation coming from the fact that we are entering into the filament and into the hotter gas of the filament. Also, what we can see is that we have roughly 2.16 differences between the two filament populations, and these differences was also hinted in observations. So maybe this is just telling us that the denser and hotter environments of short filaments, they might enhance the decrease of the star formation activity with respect to the galaxies that live in long filaments. So, in conclusion, I have built a more complete picture of cosmic filaments at redshift 0, so today. If we have here the core of the filament and here we are far away from it, we see that at the larger scales, baryons follow the dark matter distribution. Gas is in a diffuse and WIM phase. At the outskirts of filaments, we have a baryon excess, we have an accumulation of WIM gas in these regions, and the star formation activity of galaxies starts to decrease. The cores of filaments are isothermal. Baryons are depleted from these regions, maybe by AGN feedback effects. And WIM is still the most dominant phase in this region. So these are trends that are general to all the filaments, but still we have several differences between two extreme populations of these cosmic structures. They have different shapes, so short and long filaments have different shape. They have different thermodynamical properties, different proportions of gas phases, different locations in the cosmic web, and also we have hints that they have different the galaxies living inside these two different populations have different properties. Of course, I have a lot of perspectives and ideas that I would like to continue exploring. So the studies that I've been doing during my thesis were mostly done in simulations, and I used plenty of simulations with different feedback models with different resolutions in order to have conclusions that are robust. But the main goal is of course to use these results to better interpret observations. But before we are able to do this goal, there is still work to do For example, I want to better understand what's the formation history of the different populations of filaments. Is there a scale separating the different dynamics? For example, short filaments might be measure driven, and this might be different from the long filaments that might be tied to the cosmic flow following the Hubble expansion of the universe. So for this, I plan to study the evolution in time of these different populations of filaments by using simulations and retrace the formation history. Once this is done, we can focus again on the filament gas properties. So at order 0, what I would like to do is to study the hot gas. So we can compare the hot gas with observations, for example, in the SZ and X-rays coming from, for example, the new Athena or Rosita experiments. So this might be a good thing to do, but what I would like to focus on mostly is on cold gas and how does cold gas evolve in filaments, because that we know that the cold gas is the main fuel of the star formation of galaxies, and we can observe this cold gas. I mean, this study, if I follow the cold gas in filaments using hydro-dynamical simulations, I could be able to better interpret CO observations, for example, that are tracers of the hot gas in the universe, and use, of course, these studies to better understand galaxy evolution in different populations of filaments. I would like to know what's the dominant quenching processes at different cosmic epochs and also at different filament environments. And really identifying the physics that drive the evolution of galaxies by, for example, looking at shocks, looking at specific signatures in different cosmic environments. And yes, thank you for your attention.
Now, the first referee, Adrienne, if she can ask her questions.
Can you hear me okay?
Yes.
So first of all, I apologize that I'm not there in person. And I start by congratulating you, Daniela, for an excellent, extremely clear manuscript. It was a real pleasure to read it. And also a super presentation, again, consistent with your manuscript, very crystal clear, laying it all out for us. I really enjoyed it. I'll start with some questions. So the first one is perhaps very simple, I hope, and it's a phrase that you use both in your manuscript and also today. It appeared on one of your slides. So you told us that the short filaments can be interpreted as bridges of matter between overdense structures like clusters, while the long filaments shape the large scales of the cosmic web. And I found it, I couldn't, can you elaborate on what you meant by saying that the long filaments could shape the large scales of the cosmic web? What did you mean by that?
Yes, of course. So yes, we know that the cosmic web is multi-scale. We have filamentary structures not only in the largest scales, but also, for example, between galaxies. And what I meant by that is that maybe at these largest scales, the long filaments might be tied actually to the cosmic expansion, the cosmic flow, and be the main skeleton. I mean the most the robust, the main skeleton, the main. I'm losing my words. Sorry.
they might be the ones that really okay, let me. The most salient features, the most salient features of the cosmic web. That's the longest ones that are different from the bridges of matter. Okay, can you hear me well?
Yes.
Okay. That are different from the bridges of matter of between the most overdense structures. That actually they might not even be filaments, but only maybe merging process. Yes, we can see it's just a merging between two clusters or things like that.
Okay. So I was really fascinated by your measurement of the number density of galaxies, the radial profiles that you were getting. And in your thesis, you looked to fit profiles to it, and you compared it to dark matter profiles. And to me, it wasn't obvious that the number, if you counted the number density of galaxies as a function of radius from the spine of a filament, that you would get a profile similar to the dark matter. Can you expand on that? How do you explain that you are getting the same kind of similar profile to the dark matter?
Yes, so you're talking maybe about this plot. So it's something that I didn't show in my presentation, but as you can see here, for shortening filaments, we have in solid lines the dark matter density profile, and the stellar profile in this case, that basically is the galaxy number density profile, and is in here. This can be easily understood. I mean, the similarity between dark matter profiles and galaxy density profiles can be easily understood by looking once again at the baryon fraction profiles that really characterize the relative distribution between these two matter components. And what we can see here is that these two matter components are really tied up to a certain scale. That is again the limits by the R-int scale, and then they deviate at the course. So we have that here these two basically the galaxy trace really follow the dark matter skeleton, and as at the course of filaments, the baryonic effects are responsible of this deviation of this excess of, for example, of stars, because we have more stars at the course of filaments than far away.
So when do you think that profile, the radial profile for the number of galaxies, as a function of radius, when do you think that might have been established in the universe? Because here you did the measurement at redshift 0. Do you think it might have been present earlier as well? If you do the measurements at higher redshifts, do you think you'll see a similar kind of profile?
I think, of course, there will always be more density towards the core than far away. But I think that at higher redshift, so in the past, for short filaments, for example, if they are really collapsing, for long filaments, at higher redshifts, we know that the universe was less expanded, and I assume, I think that maybe the radial extension of the filaments may be broader. Yes.
And maybe I'll ask a technical question.
Yes.
I didn't understand why CP max that you were getting from disperse didn't always correspond to halos.
We are here. Yes. So why the CP max didn't correspond to halos? So it depends the type of halo that we are thinking of. We know that dispersed actually is multi-scale in the sense that it detects the filamentary structures based on the galaxy distribution. So so we will have if we have a more yes a region in space with lots of galaxies, for example, in the near the in clusters of galaxies, the filaments in size will be very short. And sorry, I forgot your question. Well, no, yes, okay. So why halos?
Well, maybe she was asking why CP max
Yes.
doesn't match halos. And maybe, I guess, Adrienne, tell me if I'm correct or not, but in your figure, you have red points which do not fall on yellow dots.
Yes. Okay, yes, so I was...
I don't know if it's the question, that's the way.
Yes. Yes.
Yes.
Thank you.
So, yes, okay, thank you. Thank you. So the red points that are not in the yellow ones, so that means that they are CP max that are in not all the CP max are lying in the vicinity of clusters of galaxies, and this I think this is just due to the way again dispersed the text the filaments. If we set a threshold here, for example, in these mountains, if we set the threshold here, we will have maybe environments that's not global overdense regions, but are just local overdense regions. And CP max, and disperse will identify them as a CP max because they are above the threshold, the persistence threshold. That's why smoothing is important to mitigate this very accidented topology and try really to detect the most salient features of the topology.
Okay, thank you. I'll stop asking you questions. Thank you.
Thank you.
Thank you. I will ask the second referee, Franco Balzar. If you have questions.
Yes, quite a few. Well, good afternoon. And yeah, I share Adrian's positive comments about the dissertation and the thesis as well as the sense of pity for not being there in Paris right now. So let me have a few questions. Actually, I have quite a few, so let me cut them a bit. So both in the thesis and in today's dissertation, you basically discussed right away the results of very sophisticated radiative and cooling star formation simulations. I don't know if in the stage of preparatory works for your thesis or at any point, did you also consider simpler so-called adiabatic or say non-radiative simulations of the cosmic web to start training the model, the reconstruction model, etc. And if there are trends you think cannot be found in simpler non-radiative simulations of the cosmic web among the one you discussed today.
Okay, so for the first part of your question, no, I used directly the outputs of for example, at first Illustris simulation, then I move on to Illustris TNG because it matched when the time where this simulation was publicly released. I didn't consider other simulations with non-radiative effects, but I think that this might, of course, change the results in the way that maybe the matter will be more clustered towards the densest regions. And of course, the phase space diagram will be different of the gas distribution and the gas properties of that I found will be different if we don't consider, for example, cooling. The structures will be heated up to highest values. But I think that the simulations that I considered were, I mean, the feedback models, the baryonic models were calibrated on observations. Yes. So, you know, we didn't plan on first developing a simple model because we didn't want to develop to compute ourselves the simulations. So.
Okay, and things like this sort of bimodality between short and long filaments, do you think it would still be there in simpler simulations or not?
Okay, I don't think so, because I perform a study of for example, the illustrative simulation. Where is it? Here. So here we see that the result, the density profile of illustrative simulation is different from the others. And so I wanted to better understand the differences. And when I analyzed more in this this illustrative simulation, and I built the profiles with different bins of length, I didn't find any differences between these two extreme bins. So this actually showed me that the different filament populations was also, I mean, the feedback models, the baryonic models are important in the identification of these two extreme populations. Yes, and yes.
But then the follow-up question would be that I'm not sure I understand the physical explanation for these two classes, because it looks like it has to do with the environment. So shorter filaments are denser, puffier, they are in regions with high cosmic overdensity, big clusters, etc. But all of that, in principle, should be on scales which are rather unaffected by all these baryonic physics, which takes place on scales of galaxies, say. So can feedback really affect the properties of filaments on scales of tens and tens of megaparsec?
Yes, I think yes, it can, because we know that feedback effects are really important. For example, in the distribution, in the clustering of matter, even in larger scales. For example, if we look at the matter power spectrum with AGN of simulations with AGN and with simulations of without AGN, we know that we see that there's a power deficit even at scales of more than 1 megaparsec, roughly 1 megaparsec. So yes, I think that even if this smaller scale physics can have an important actually impact on the large scale distribution and the properties of matter in the larger scales.
Okay. And you briefly mentioned towards the end of the dissertation the application towards observation. So, for example, there was also a recent claim of the detection via stacking of the X-ray signature of filaments. Did you try also to replicate that as well after the Sunaya-Zeldovich say comparison? Is it something you plan to do?
Yes, so I didn't do it, but I think it's interesting to do such things. but in a less dirty way than for doing this okay, for being able to actually compare results from simulations and observations, we need to be in the same conditions. So for example, use a light cone, replicate the selections effects in, for example, for detecting the filaments, we have to be dealing with the same galaxies, for example, with so there, I think in order to compare results from observation of for simulations with observations, I really need to push a step forward and do, like, for example, mock catalogs that are really mimicking what the observational constraints of a given observation. In this case, for example, X-rays. Yeah.
Okay.
So it's,
and moving.
Yeah. Sorry.
Sorry. And you also mentioned you would like to move onto the territory of cold gas because this is what is feeding galaxies, for example. In that case, which would be the ideal either existing or future observatory or survey if you have to try find the observational counterpart of that cold gas that you can find in simulation but that won't shine in X-ray?
Yes. So for cold gas, I think we will need to look at higher redshift because that's where we have the peak of star formation. I would think of observing, yes, as I said, the CO emission, maybe H alpha as well. I'm not sure of. Yes, I'm not familiar with the types of instruments that I could, or types of telescope that are actually working with that with these types of observations, but that's what comes to me now.
Okay. Final question. So in this thesis work, you applied this reconstruction technique and very sophisticated analysis to simulations that were already there. Now, suppose in the future you can get infinite or enormous computing resources, what would you do to move forward? What do you think might be having infinite access to computing resources the most interesting thing to do to follow on this line of research?
Oh, okay. So if I would have unlimited time, or computational time and resources, I think I would like to create a simulation with like a very big box volume, simulated volume, but going really into the scales of the, I mean, with resolution, able to go, for example, for cold gas, there has been recent studies that tell us that we need to go to resolutions of the order of a few kiloparsec in order to really really be able to probe, to see the cold gas profile, the cold gas profile around the filament. So I think we need to increase both resolution and statistics. So the size of the box to be able to, I mean, it would be perfect.
Okay. Okay. Thanks. I am done.
Thank you.
Thank you very much. Françoise?
Oh, okay, so thank you. So I want also to congratulate you. May I say this? Okay. Congratulate you because the thesis was very interesting and you did a very good job and very important job, and your presentation was very clear and very interesting. So also I have a few questions, in fact many questions that sorry.
No,
You should take your time.
Okay.
I mean,
So-
I should have said it at the beginning.
Okay.
It's our
So-
moment, and it's a good moment to have interactions on the subject. So as long
But-
as you want.
So the first one I would say is the determination of filaments. So you did a good thing because you were doing that from galaxy catalogs, exactly like an observer would have done it from galaxies. But since, so this is a good point, but then since you have a simulation, I have seen also very interesting to have it from the density. You have the dark matter, the density. So it would be even better for the Morse theory because you have a continuous derivative and so on. So you have to build a discrete things for galaxy numbers. But here, why not? Have you tried to do that with only smooth density?
Okay, I tried, but even in simulations, the distribution of dark matter is still discrete because we have the positions of dark matter particles. Okay. We have the distribution of dark matter particles, which they are particles. So we still need to go from this continuous from, sorry, the discrete to continuous with the Delaunay. So I tried to apply this first to directly the dark matter particles, but since there are billions of particles in, for example, the TMG 301 box, it was computationally very, very expensive. And the result was not satisfactory in the sense that, as you may imagine, the dark matter particles trace really everything. So I got skeletons that really had a very, very short filament.
But you can smooth like you did.
Yes, yes, I could smooth, but also this increased the computational time. And yes, I think if we want to apply the to have a skeleton, to have filaments directly arising from the dark matter density field, disperse might not be the best option, but for example, Nexus might be better because it defines the filaments, the features of the skeleton with a different way. So in the case of Nexus, is computing the adhesion of the field. So it's another type of definition of the filaments, but it has to be adapted to what we want to study.
Okay, so now you have some behavior of the dark matter galaxies according to the distance from the filaments, but also at the density is the same as the proxy because the density is going down. So have you tried to do a study from density, like a Dressler et al. Study, that you have galaxy properties as a function of density of the environment without looking at filaments?
Yes. So no, I didn't try. But that's what I would like to do as well. Focusing, okay, if we take this galaxy that is living in this environment, what are its properties with respect to a galaxy that lives in a completely different environment, and see if we can. That's how we can see that how the environment has an impact on the properties of galaxies. But there are plenty of studies that have already been doing this with filaments. And that's how we know that, yes, I mean, that there are a lot of studies in observation and simulations. But what I really want to do is better understand what are the mechanisms, not only okay, we see a relation between okay, galaxy. We have more red galaxies in hotter environments or in denser environments with respect to less dense and colder environments. But we need to better understand what precisely is what are the interactions between the galaxies and the gas. If these interactions are really coming from the environment or not.
So for the two sort of filaments, the long, short, and so on, Have you also tried to look at the velocities of galaxies inside? Because then the long we have the impression that the velocities are higher. Or...
Yeah, so what I did, so I'm unfortunately I didn't put that in my presentation. I did look at the velocities of galaxies again radially, how what's the mean velocity of the galaxies at a given being with respect to the distance of the filament. And what I found again is that in short filaments we have a huge. I mean, galaxies are the velocity norm is larger by, I don't remember, but maybe a factor of I don't want to say, but yes, in short filaments, galaxies are the norm is of. I mean, it seems like galaxies are going faster towards short filaments.
So the lifetime of filaments will be different. In fact.
Yeah. That's why we need to better understand how they formed and how they the dynamics around them, how the matter is being affected. Yes.
Now, there is also a very interesting point here, well, in the previous slide, where you showed that there was a deficit of baryons in the center.
Yes.
But what the question is I had is that have you taken into account the galaxies? Because for the filament, you have removed all galaxies clusters, and normally you should not have any different baryon fraction than the universal one over 1 or 2 megaparsec. Well, it's like in clusters, you remember the White argument that over 1 or 2 megaparsec, there is no different baryon fraction than the universal one. So have you tried to add all the baryons that are in galaxies, groups, and clusters to see that if the baryon fraction is the same in the core of filaments?
Actually, the plots that we're talking about this.
Yes, all this whole, is it filled?
Sorry, what?
No, the galaxies are not taken there.
They are.
Because you said that for the gas in the filament, you remove all the clusters, groups, and galaxies.
Yes, sorry, maybe I was not as clear as I wanted. For this study, I included, I mean, if I'm comparing with the cosmic fraction, I want to take all the matter. So here so raw gas is raw gas total and with the gas inside the galaxy as well.
So then this mystery, why is there such mystery?
If I can just when you say R equals 1 megaparsec here, and you are at close to the universal baryon fraction, yes. Is it integrated up to 1 megaparsec, or is it in an annulus of 1 megaparsec?
In an
I interpreted in an annulus.
That's the point. I mean, if it's integrated, then it's okay.
No, it's not integrated.
It's annulus?
It's annulus, yes.
So if you are integrating up to 2 megaparsecs, for example, you would be missing baryons.
Yes, because if this is something I put in the manuscript, not in the presentation. Actually, I found the cosmic fraction when I integrate up to 7 megaparsecs. So here, that's where I found
So maybe it's a difference between a simulation and observations. Because in observation, we don't see that. We have the impression that the galaxies and clusters, well, a cluster, for instance, you have the baryonic fraction. Normal baryonic fraction, groups also, and so on. So in general, maybe it's a difference between simulation and observation. It's possible.
Maybe it's just yes, the way it's computed, because here I don't know if in clusters you integrate it.
Yes, you have all in a cluster for 1-2 megaparsec. You have all the X-ray gas, which is most of the baryons, and you retrieve most of the baryons. You have not this whole. Yeah, but anyway.
Okay. Yes, just to be clear, this is being by being. So.
Mm-hmm. And I was wondering also about all, maybe in the simulation, there is not all that we measure in observation, the ram pressure action that, well, because there is AGN, of course, and we can feedback that the simulation at least use and abuse. But in reality, there is a lot of run pressure stripping of gas. So maybe some part of in the observation of gas motion should be done by this, that you remove all the gas in the galaxy in a cluster. Even in filaments, it's observed. We see that in filaments, we have around Virgo, for instance, we see a lot of jellyfish galaxies in coma, that all the gas is going out, and there is only ellipticals without gas in the center. So maybe there is something like that. But do you think that in simulation they are able to follow the run pressure stripping exactly or not? Just an opinion. It's not a question.
The question is, or the opinion.
Yeah, your opinion. You think that is only as a non-gravitational physics, only AGN feedback, or do you think that the run pressure stripping can also move the gas?
Of course, run pressure stripping can also move the gas.
But in the simulation also?
Yes, I think so, because I mean, I'm not saying that all the question here is due to AGM. I just investigated AGM because I wanted to see if these very powerful astrophysical processes could have an impact, could be powerful enough to do this. So that's why I started with this. But of course, I think that there can be plenty of other processes, like yes, versus stripping. Yes, of course.
Finally, well, you spoke about cold gas, and indeed you're right. There's a lot of cold gas, and recently in the simulation, when you have enough resolution, people realized that there was a lot of cold gas accretion instead of warm gas that were cooling down, but it's directly accreted cold. So do you think that these simulations, well, at least illustrates with this resolution, are able to see the cold gas? In fact, it was 10 to the 5, the maximum or
so
minimum?
I don't think we can come back to the first place. I don't think that this was, I mean, that there is the TNG 301 simulation would be able to give the best, would be the best choice to study cold gas, because cold gas happens. Cold gas is, we want to explore smaller scales. Maybe, okay, there's another simulation of the same series, the TNG 50. So it's a much smaller scale. I mean, it's only 50 megaparsec of side length, but here the resolution is much better to be able to really dig into this more smaller scales of the.
So you could do smooth zoom in simulation.
Zoom in simulation, of course.
To have this. Okay, so thank you very much. It was very interesting.
Thank you, I will ask Pekka in a minute.
Okay. Thank you for the presentation and the well-written thesis. It was very clearly written and it was very nice to read it. Even I understood that very well. So I have a few questions, and the first one could be that kind of general question that can you bring out some limitations or weaknesses or uncertainties in filament extraction method, and also maybe these simulations that may affect your results, and can have you any idea how to fix them if it's possible?
Okay, so concerning the first part of the question, so the question was what are the limitations that I have with this filament section method? So first first, as it's shown here, it works the topology of the density field, and as a consequence, we can have things like this, where the maximum density critical points are not necessarily corresponding to the main structures, the real physical structures of the clusters. And so disperse with this by computing the topology of the field and setting the threshold, can locate the CP max in regions that are not necessarily massive structures, and add maybe contaminations of filaments that are not the large-scale filaments that I'm interested in. There are other methods, of course, for detecting filaments. Each one is based on in a different way, as my colleague Tony presented yesterday. But for this study, I used disperse because first it was when I started my PhD thesis, when T-Rex was not done yet, we started together, and we wanted an algorithm to be applied to the distribution of galaxies to be able to compare with observations, to also to be able to trace the sign. So yes, yeah. And the second part of the question was concerning the simulations. So again, there are plenty of publicly available numerical simulations in the market. I used mainly the PNG series, also Illustris, in order to compare with a different environment model. I also used Magnetica, but there is also Eagle, Horizon IGN. There has been a study of gas in the Eagle simulation by our Estonian colleagues, and they have found similar results concerning, for example, the properties of wind in filaments. So I think that as long as the simulation is robust enough, calibrated in observations, and that gives that it's managing to reproduce for example, the mass function of galaxies, the luminosity function, and yes, as long as these constraints are well defined and well respected, maybe different simulations may lead to similar results.
Yes. Then is you have in your talk, page 27, you have that kind of yes, you have this radial profile of the filament there, and then you have this segmentation of the filament, and if I understand right, that you need this segmentation along the filament length because the diversity of the filament, we know that there are very diverse structures along the way, and you must make that kind of segments, and then you average size and so on. But how you decide this segment length?
Okay.
What is that?
Yes, I don't decide it. It's the way disperse defines the filament. So so imagine you have a distribution of points, you compute the Delaunay tessellation. The Delaunay tessellation is just a way of going from a discrete distribution to a continuous one. So each point is basically a vertex, and you have ridges of these trihedrons. And imagine you have 2 points. One is a maximum density critical point in the saddle, and the filament will just be the ridges connecting the different tetrahedrons going from these two different connecting these two points. So that's what I call the segments. So the length of the segment depends on the underlying density, of course.
Right. And next. Second life. So it's something what I thought to ask. The distribution, length distribution of those filaments. Was it so that shortest filaments were something like 0.4 megaparsecs? Does it mean that some of those filaments are thicker than longer? Or
Sorry?
There's very short filaments.
Yes.
Does it mean that some filaments are thicker than longer?
Well, no.
No.
No, actually, when I say short filaments are here about yes, it's 5 megaparsec, I'm talking about the mean profile. So the average profile. Sorry for it's very important. So it's the average profile of all the filaments that are here. Yes, so this is the average profile that actually we can see here, and this is how in average these filaments are short ones. But if you take, of course, the filaments of
0.5,
0.4
0.4 megaparsec.
Voila, of 0.4 megaparsec. First, I don't think they are large scale filaments.
Yeah. So
And
what are they?
that's the thing is that maybe it's it comes from the way dispersed the textile filaments. They are just maybe there are filaments that are very in regions that are so dense that locally you have a lot of variations of the density field, and these filaments are and so in these variations of the density field you have a maximum density critical point in the saddle and a very short filament. That's the filament that I actually tried to clean from the skeleton. And in my thesis, there's this chapter with a lot of technical things in which I assess the impact of the smoothing and the persistence of the dispersed parameters, and also so I let me just remember my thesis. So that's where, yes, before okay, this is the breakdown. Yes, the raw output of disperse gives me a lot of very spurious filaments, which I cleaned by reconnecting the filaments in order to really have filaments going from maximum to saddles, because the raw output only gives me filament portions. So the initial length distribution, I just take what disperse gives me. You have a peak at 0 actually, and when I do this work of reconnecting the filament portions to really have filaments going from maximum to saddle, this peak is erased, but because you still have some very, very short filaments. That's how
Yes.
sorry.
There's page 38. Yes, you have this nice bump here, and this is also prominent in same distance from the center of the filament. It's also prominent in temperature profile. And my question is that if we think that kind of shock front of the incoming gas around the filament, is there some kind of can you imagine some kind of observational way to maybe try to detect this kind of shock front?
Okay.
Maybe front coming observational method.
So you think, sorry, you said that the bump is seen in the temperature profile, but
it's not seen, but it's
okay.
increased dramatically in this point. Yeah, same.
No. So the bump, if we put the scale, the radial scales together, the bump correspond that.
Yeah, here. Yeah, okay.
The temperature starts to increase.
Yeah, it starts, okay. But it's reached the maximum there, that same distance. If you put back that, so you have that bump here. So that is and you wrote that this might be some kind of shock front.
Yes, the wind being assembled at the filament.
Yeah. So I start to wonder that maybe there might be some way to observe that kind of shock front. And there's some at least trials in
yes. Okay, I think.
What kind of, can you mention some way how to, because it's important if you have this kind of theoretical prediction that you have this kind of shock front, and this is statistically there. So it would be nice to have some way to verify theoretical results using observations. So can you mention it?
Okay, so I think. So this shock front, first we really had to dig into the dynamics to see if they're in simulations and see if we find signatures of shocks. So we have the vorticity, for example.
In these simulations, you have gas velocities.
Yes.
Yes. So in principle, you can verify these using also gas velocities.
So this would be the wind gas, and I think maybe one of the best ways of seeing the wind. So it's gas that is diffuse, it's might be hot. I think we can do CSZ signal again, but with a higher resolution. For example, your future ground experiments.
There's one thing that's just come to my mind that maybe in future we will have those. We know that there should be those cosmic magnetic fields.
Yes.
And the future radio observations using, for example, SCAR could be that way to detect that kind of shock fronts. When you have this synchrotron radiation, this magnetic field,
yes,
if you have that kind of prominent, I don't know which
maybe yes.
Great. Thank you. Marius.
So Daniela, congratulations on a very beautiful written thesis and on a very comprehensive study of the filaments. And I think you did a good job, summarizing this in a very clear and concise way during your talk. And I can imagine it wasn't very easy given the wealth of information you have in your thesis. And I just wanted to say that it was a pleasure to actually read your thesis and the thorough analysis, and especially to the insights that you actually gained from the analysis about how the filaments, property, galaxies, and gas are connected, and so on. And in particular, at least my opinion is that the excellent thesis is really one that ends up raising more questions than actually it answers doing it, because it kind of tells us and points out, that how ignorant we are, of the wider universe, that there are really much more things that we don't know. And that's why I hope, like my next few questions more focus on the, questions that actually your exemplary work raises, and not so much, like on what you did. And I think one of the first question that I will ask, and you probably know already a bit my point of view, is that, so one way in which you probe the diversity of filaments was to show, that the short and long filaments have different profiles. But do you think, is this the best way to do it?
I think it was at least the best way, given how I define the filaments using disperse. So because disperse is really sensitive to the density field, it defines the filaments with respect to the topology, and as I try to explain to Becca, the length of the filament is directly a tracer of the so the length of the segments is directly tracing the density, and then if we connect the segments, we have the length of the filaments, and then that's how it's connected to the environment. But of course, we can use, for example, the width of filaments, the puffiness of the filaments are also probably the tracers of different environments. For example, I know that there have been several studies that have also divided filaments into different categories, taking, for example, the puffy filaments with respect to the thin filaments, and showing that the spin alignment of the galaxies living in each one of these different environments is different. So again, showing that this continuum distribution of the filaments that I showed to you in the introduction can be seen in a different perspective, not only with length or density, but also with the other filament properties. Also, there have been studies that again have separated filaments with the luminosity of the filaments, so of the galaxies living in filaments, so separating high luminosity density filament from low luminosity density filament. So these are again related to the environments, because we know that the more luminous galaxies are living in denser environments. So yes, I mean, I think we can imagine a variety of ways of cutting a continuum in 2 or 3, but yes, in this case, length was the most natural, the obvious choice given the way.
So follow-up question: if you were to start now the PhD in Abder's group, would you still use disperse, or maybe would you use a different filament finder, and why? And let me underline, there is only one correct answer.
Yeah, of course, I would use T-Rex.
But is there a reason why?
No. Okay. And more seriously, if I was to start my PhD thesis again, I have to just thinking about it. I think I will use an algorithm that disperse is very I will use an algorithm that is really optimized in detecting cosmic not, for example, what we were discussing with Becca is that this bird gives me a lot of spurious things that we don't know really what they are. We can clean them by setting the persistence threshold, but if we raise the persistence too much, okay, we have the main features, the main the main the basic filament, like really the basis of the cosmic web, but we lose a lot of information. So that's something that is not happening in other filament binders, for example, Spherics or Nexus, when we can really, they are really adapted to, I think, more astrophysical studies.
And I have another question. This is about the Soutenance part. So you compute the Soutenance signal from filaments, and then what you find is that it's actually dominated, if you look here, by the signal from basically gas in heros.
Yes.
Yeah. But if you really want to measure the signal from just filamentary gas, how would you do it, like in observations?
I really want to measure the signal.
Because here the contribution from heros is basically like, let's say, a factor of 5 larger than just the gas outside the heros.
Yes.
So if you do a measurement, you are really always dominated by what happens inside the heros. So how would you, is there a way of maybe just being?
Yes, I mean, but the way people have been doing it and the way it's done in this paper, yeah, it was, I mean, they masked the failure. So it's really you take, okay, the wide map, and then you locate the position of galaxies or massive structures by using galaxy survey. So then you mask, you match the positions, and you mask the regions where
Okay. That's the exact answer I was looking for. But and now this comes my next question. So how deep would you have to go to be able to really remove, most of the contribution? Have you looked into that? Because, well, potentially you want, to be able to remove heros above a certain mass.
Yes.
Because those will be the ones. But have you looked into that? Or?
No, one of my list is to perform a study. Yes, with, for example, increasing or decreasing the mass of the halos that I mask, because in this study I mask the halos that are massive than 10 to the 12. It's written somewhere, I don't remember. But yes, it would be very interesting to for example, set bins of mass and then mask each bin and see how the signal evolves, and then be able to, for example, really compare that with the observed signal and check, not check, but interpret what kind of contamination or contribution from gas in what type of halos are we looking at. Or not, or maybe it's really, but we have to be careful to with these observations, because again, here I did not study, this is at redshift 0, these observations were done at a bit higher redshift. So we need really to be in the same conditions to do such analysis.
And one last question, a bit provocative.
Oh.
So your thesis is based on hydrodynamical simulations.
Yes.
Can we trust hydrodynamical simulations? And what does it mean for your results?
So I think maybe 10 years ago, when we started, well, I was not here, but you started to get interested in yes, knowing how galaxies evolve, and the community wanted to better understand it. And so let's go look at numerical simulations. I think at that stage, at that moment in time, the numerical models, the prescriptions were not ready enough, were not solid. Maybe they didn't match yet the observations. And since then, I think there has been a lot of improvements, and people are still working on how to better implement astrophysical processes. For example, we have AGN feedback or stellar feedback, or how the cooling, the magnetic fields, how to implement this in the recipes. What's the best recipe for having information and conclusions that we can trust. I think now we have reached a point where these recipes may be trustable. They have been tested with comparing with several observations, and yes, I think we can trust the hydrodynamical.
It's clear that they're not perfect, but I think,
Of course,
I guess my opinion is that it's the best tool that we have in the moment from the theoretical perspective. So, thank you.
Thank you. I will also ask a few questions, and then I want also to congratulate you for your presentation and your manuscript. And I personally enjoy very much this topic, so I think it's a very exciting topic where we have a lot to learn. I don't want to be too long because we've already had a lot of discussions, but I've taken note of a few sentences that you said, and since you're going to continue research, I wanted to play a kind of mirror effect to send them back to you. So it's you speaking, not me. Huh? I do not decide what is a filament. It's disperse which decides. Disperse gives me, but I don't think that the shortest filaments are filaments, but merging between two clusters. I won't comment. Just remember that, because at some stage we have to have some control on the machines, otherwise Terminator will arrive, you know? So to be more specific, and I won't be long, but just let's go back to this slide 23 that we saw a lot. So that's where at some stage you said, I believe in the output because it's robust and reliable. So you are in your office, you are working on your PhD, it's a Tuesday, it's 10 a.m. You have your results, and then you end up with this conclusion. This is robust, reliable, and from now on, I'm going to trust what Disperse told me. Those are filaments, and I'm going to speak about short and long filaments and everything. Remember this Tuesday, 10 a.m. Go back there. Tell me, how did you convince yourself that the 91% criterion of the 3 sigma sharp was it? That Tuesday. How did you convince yourself? Because there will be more Tuesdays to come. And you have to have weapons in front of these things because people will want to quantify the sharpness of the robustness.
How did I, okay, that's back to that Tuesday 10 a.m. The thing is that, okay, here I put search for 3 different sequence versions. I stored also, for example, 2 sigma skeleton. And the way I convinced myself was by performing a comparison between the different outputs of this person.
Just let me help you. You're talking about completeness, right? That you want to have the maximum fraction of clusters found. So we call it completeness.
Yes.
Okay, so you have completeness. Now there is another criterion that we often associate to completeness. because there is always a price to pay. You could be 100% complete, but you could be 75% impure. So what is the purity of your sample? And if you want, I can tell you what I mean by purity, but do you see what I mean?
Maybe a reminder.
The purity is that to get 91% of the clusters, you may produce 45% of fake ones, which are the red points which are outside of the yellow ones. And since filaments are connecting the red points, you may have fake filaments. And you want to quantify the fraction of false peaks and filaments to convince yourself that you are in a robust regime, not simply completeness. So let's say it may be something that happened at 11 a.m. or something. How did you convince yourself that the price to pay was okay in terms of having these red points flying around?
Okay. Concerning the red points flying around, here I don't show it in the presentation, but the fraction of red points really flying around that not correspond to any halo, it's very minimal for this system. And the results perform worse. I mean, not as optimal as the skeleton for other parameters. So I just chose among the choices that I had. I wanted a catalog of filaments. I applied disperse with different parameters, different smoothings, different persistence threshold, different combinations. And at the end, I just compared the outputs and chose the combination of parameters that was the best among my different results. Of course, this, the results might not be the actual, the true, I mean, tracing really all the features, the topology of the density field, but it was the best compromise between all the different parameters that I have. That's how I decided to use this to do actual studies of the matter and the properties around.
I just have a second question.
Yes.
The second question is, you have your distribution of filaments.
Yes.
With your different, I mean, your histogram. Yeah, yes. If you can just, it was not. Yes, that's one. And so you look at this distribution, and then maybe it's a Thursday or I don't know which day, you see, oh, I can see two populations here, short and long.
No.
Well, how do you make the bimodality between short and long?
By looking at the way the matter is distributed around the
yeah, but it's a continuous distribution.
Of course,
but so why do you make a bimodality? Why did you prefer a bimodal distribution, since you know that the ones which are very short are not true, they are connecting clusters and stuff?
No, I'm not saying, sorry.
Why didn't you, like, say, study three populations, like short, medium, and long, or a continuum, and then measure a kind of parameter of that would be an? Why did you think that it could be useful to split in two, for example, since it's not a clear-cut bimodality?
Yes. So there are two answers to that question. I mean, two parts of the for your question. First, let me come back again to the initial motivation. That was, okay, we see a huge diversity in the densities of the filaments. There are filaments that are have densities close to the nodes, so very, very dense filaments, and other filaments that are densities close to the typical densities in poles. But we are calling these two very different objects filaments. So how is that possible? So are we looking at the same object? Is it the same beast? Okay. When I analyze the distribution of matter, so of galaxies around around filaments, and I explored the variation with length, I saw that there are differences. And the way I quantified is just I want to see what were the extreme behaviors. We had extreme behaviors, for example, filaments in with density similar to null, filaments density similar to voids. I also wanted to see what are the extreme behaviors of and the properties of these extreme filaments in terms of the length. So that's how I decided to look at the extremes of the length distribution. That, of course, is a continuum.
And so that just to finish on this, is just like, could you imagine that, for example, you could have short filaments that you would not see if they were not connecting most massive clusters and everything, and therefore you could have a selection bias such that the reason why the short filaments are more puffy is because if they were less puffy, you wouldn't see them in disperse. Or let's say, in other words, disperse wouldn't tell you they are there. Because to see them, if you have a very short filament, to get the signal-to-noise ratio for disperse to see it's a filament,
yes,
maybe it may not be as easy to see if it was not fluffier. So maybe there is a selection effect. It's a question. Could it be a selection effect that the width of the filament is bigger for the small ones because you need a minimum number of points or whatever, and therefore it's when you have higher density of points that you can see short ones, but if it's more, if you have less density of points, maybe the software cannot see a short filament because of the sparsity, and therefore you can have a selection effect entering into the game. I'm not saying it's true. It's a question. Maybe no. Maybe it's not.
I don't think I actually understand your question.
Oh, maybe I'm not. Maybe it's not a good question. I don't know. I mean, I'm not even sure the question is good. Huh? So.
Okay, yeah, I can answer to the question. I think I understand.
Take this one.
Okay. So, what if I can rephrase your question?
Yeah.
Okay. You're saying to me that maybe the very short filaments will not be found by disperse
Unless they are fluffy.
Unless they are
they are fluffy.
Does not give me a measurement of the.
No. It's not that it gives a measurement, but it may be biased by some. Let's keep it for later. You see, I'm wondering whether there could be a bias that explains why they are thicker, because you need more points. But
bias. Sorry, maybe we can
discuss later.
I'm sorry, I don't think I understood.
Thank you very much. And now I'm going to leave. So I don't know in which order you want to speak.
Come to you, Mathieu.
Well, maybe I can begin because all these projects actually under the patronage of Daniela, and the same set of projects that belong to the biopic project. So thank you very much, Daniela, for actually giving me this opportunity to work on very interesting topics which involve the physics of gas in cosmology. This has been for a long time actually a topic that has been ignored or actually put aside because it's a complex physics, and as I think many of the people present in the jury have mentioned, you have started exploring the complexity of the physics of the baryons in the cosmic web from the point of view of actually trying to classify everything to get a comprehensive picture of the gas on large scales. And when I remember the first time we met, that was a very long time ago. You were well, not a kid, but almost in my class in quantum physics at the bachelor level, and you made a long way up to today, and I'm deeply moved by all your accomplishments since then. I enjoyed very much, and I benefited from your tireless efforts to map, understand, discover, uncover everything and even more that you could. I'm sure that if you had more time, you would have actually continued exploring even more effects in those simulations. And I hope you will, and I hope that you will continue in that direction, and that you will keep us in the loop, because it's very interesting. And thank you for your enthusiasm, for your curiosity, and I wish you all the best in your next endeavors. Thanks.
Merci. I'll speak in French, if you don't mind. You don't mind? Thank you. I'm asking my colleagues. Oh là là, je suis émotionnée. Donc, je voudrais te remercier beaucoup, mais je voudrais aussi surtout te féliciter pour tout ce travail que tu as fait pendant ces 3 ans. Un travail que tu as mené de bout en bout, que tu as mené d'une main de maître, qui en fait nous a permis effectivement de comprendre un peu mieux comment se caractérise la matière, en particulier le gaz, hein, comme l'a dit Mathieu, autour des filaments. C'est un sujet qui était immense, qu'on a posé un peu comme ça sur la table. Et grâce à ta détermination, grâce à ton enthousiasme, grâce à ta rigueur, grâce à tout ton travail, tu as réussi à faire que, pour une fois, une thèse que j'encadre ne part pas dans tous les sens et tu as gardé le cap. Donc ça, c'est quelque chose de fantastique et c'est quelque chose pour lequel je te félicite, parce que le mot est vraiment là, tu as gardé le cap. Tu as gardé les questions principales, tu as réussi à mener en fait tes recherches, tu as rajouté tes touches personnelles, tu as rajouté tes questionnements et ta curiosité, ton enthousiasme et ton travail ont fait la suite. Ta capacité à collaborer avec les gens, à interroger les gens, à aller chercher les expertises là où il fallait, a aussi été un trait de ton caractère et une de tes qualités scientifiques et une de tes qualités de chercheuse. Donc, pour tout ça, je te félicite et je te remercie aussi parce que du coup, on a passé un temps super. En tout cas, moi, j'ai adoré toutes les discussions scientifiques qu'on a eues à 2 ou à 3. Mais il n'y a pas eu que ça, il n'y a pas eu que de la recherche, il n'y a pas eu que du travail scientifique. Il y a eu aussi ta générosité et ta participation à la vie de l'équipe. En fait, tu as été un acteur, un des grands acteurs de l'équipe, justement faisant lien avec les gens, toujours avec enthousiasme. Tu as participé au-delà de l'équipe à la vie collective. Tu as représenté les doctorants de l'école doctorale d'astronomie et d'astrophysique d'Île-de-France. Et tu l'as fait, je pense bien, m'a-t-on dit. Et tu as aussi aidé en répondant aux questions à toute une génération de jeunes qui postulaient à cette école doctorale en leur donnant des conseils, en les aidant de manière absolument généreuse. Et il y a tout le reste, toutes les discussions qu'on a pu avoir, le partage d'une expérience d'expatriation qui n'est pas toujours facile, loin de sa famille, en particulier en temps de Covid, ce n'était pas facile. D'autres aspects encore plus personnels hein, que je ne mentionnerai pas. Et puis après, je me suis dit, bon, alors, qu'est-ce que je peux dire et qu'est-ce que m'inspire Daniela, ces 3 ans, qu'est-ce que ça m'inspire? Et j'ai été piocher, pour ceux qui étaient là hier, bon, ils verront quelques commonalités, non pas dans Harry Potter, bon, toujours dans de la cinématographie, toujours de la cinématographie des moins de 13 ans, ceux qui me connaissent comprendront pourquoi. Et en fait, j'ai été piochée, ou en tout cas, je n'ai pas été piochée, finalement, c'est venu tout seul. Et ce qui est venu tout seul, c'est le titre d'un film animé qui s'appelle Vice Versa en français, Inside Out. Et j'ai pensé à joie. Et voilà. Et j'ai trouvé que ça te caractérisait parfaitement bien. Donc, j'espère que tu garderas cette caractéristique, en plus de toutes tes qualités scientifiques et professionnelles qui vont croître et grandir dans ton futur postdoc. Et je te souhaite tout le meilleur pour la suite.
Alors, avant qu'on se réunisse avec le jury, on demande toujours s'il y a une question dans la salle. Tout le monde a très bien. Ça veut dire que l'exposé était clair, donc ça confirme.
Je pense que je vais demander à Mathieu de se connecter au Zoom pour, si tu peux, pour qu'on ait un host et on indiquera à Céline. Sorry, I'll switch to English. Sorry for the colleagues outside. So we have to move to another room. And yesterday we had an issue with the Zoom which broke. So I think that we will leave Céline as host. And once either Mathieu or me are connected, or maybe the president of the jury, then you disconnect. If it's okay. Okay. So we're going to move. Yes. So we're going to move Adrian and Franco to another room.
C'est nous qui partons. agreed that you gave a fantastic presentation, which was very clear, very concise, which reflects that you did a huge amount of work that combined both big data analysis as well as new techniques and using the latest numerical simulations of the universe. We noted also that this is a very timely PhD, both because we need it, but also because it wasn't possible before. And it was a clever way to digest this huge amount of numerical data. I mean, maybe you didn't think you have it was easy to digest, but it was a clever way. It's easy for us to say, but we know what it is because we have seen the field increasing and increasing. So new students arrive with even more things to learn and to digest. So that's why for us, it's always impressive to see this huge amount of information. Your advisors say that they witnessed fantastic progression in your maturity, in your independence, and they told us that you will continue in the postdoc. So we can only wish that you continue to grow and bloom like a flower. And we have noticed also that your work combines many aspects of analysis, statistical analysis, physical interpretation, sometimes using back of the envelope calculation, sometimes sophisticated numerical and analytical analysis. You did a very nice synthetic presentation and in your manuscript, and which is very pedagogic, which shows that you're also very able to teach and to explain things to everybody. So we all agree that we want to wish you the best in your future career in astronomy, and that you've proved that you're one of us. So congratulations.
I will remove the mask. Well, thank you, David. Thank you, Françoise, Pekka, Marius, Adrienne, and Franco that are not here, but there. I will talk about you later. Well, thank you for being here. Thank you for all the time you spent reading my manuscript and asking me the questions. I really enjoyed this small discussion with you. So I have a lot of names that I want a lot of people that I want to thank. First, thanks to my family, my brother here, Celia. Unfortunately, my parents are not here. Gracias, papis, abuelitos, Cami, por todo. I miss you so much. Thank you. Oh my God. Thank you.
There is no.
Thank you, all the EIS team, the cosmology team, so all the staff members, and most particular the PhD students, Tony, Marion, Thibault, who's not here, and Adélie, that was my my friend in the bureau upstairs, and we put music out loud because nobody can hear us. Thank you also those who left, Louis, Victor, you really were important for me. And most of all, thank you, Celine. I don't have words to thank you. Thank you, Natalia. Thank you, Alex here, and all my friends from the master. I arrived to Orsay 6 years ago, and I met a lot of people, but I'm still in contact with, friends that are now like my brothers and sisters. I'm thinking about Clément, Emeric, and also people that are not here. Thank you to les colloques. I think the thesis will not be the same without you, of course. You really are my brothers here in France. Thank you, Andres, also for all the opportunities you gave me. We organized a workshop together. It was amazing. I hope we still be in touch. Edouard, Hideki, Laura, everyone, thank you. And most of all, thank you, Mathieu and Nabila. Mathieu, we had, okay, you told everyone that, yes, we met when I was like this, but I remember the lecture where you arrived. So Mathieu was my quantum mechanical teacher. And he was very upset with our results, with our scores in the first partial of quantum mechanics. And here it was not possible, you don't listen to me. And he was very upset with us. But then I think we studied a bit more. and I really enjoyed all the discussion, the scientific discussion, all the sports we did together, the Swedish feet, the discussion about everything and not only science. It was really interesting. I really appreciate the time we spent together during these 3 years. And Nabila, I also don't have the words to thank you, Nabila, because you know everything. Now everything that I have been through during these years, and thank you for your, of course, your scientific support, your advices, not only in science but in every aspect of life. You were there for me. You were amazing as a supervisor and also as a human. That I know we can count on you for everything. And yes, so thank you all very much, and I'm so happy to share this moment with you. And Florian, sorry. And yes, so we can. Oh, Pierre, I almost forgot Pierre. Pierre is the guy I shouldn't forget because he's the reason why I'm in astrophysics. So when I was in L3 physics, I didn't want to do astrophysics. I wanted to do particle physics. And then but I also hated all the experimental physics. I mean the TP. So I was with my friend Louise, who's not here unfortunately, and she was like a big fan of astrophysics, and we were in Binom for doing a project. But I didn't want to do the Arduino things about the touching things and des verrous et des trucs comme ça. And Louise wanted to go to the Coupole d'Astrophysique to have a project on the way the studying Jupiter. So I say, okay, if you can save me from these experimental things, I'll go to the Coupole with you. And that's how I was in contact with the sky, and I measured how Jupiter turned around and the speed of turning. And Pierre was my supervisor, and now it became my friend. And thank you for all, Pierre. So yes, there's a depot with food and drinks, of course. And I hope you can share it all with me. And thank you again for being here.
just like to say something. Je remercie énormément toute l'équipe des jeunes qui a organisé pendant toute cette semaine. Toute l'équipe des jeunes de l'IAS, doctorants et postdocs, qui en fait a pris en charge d'organiser toutes les soutenances de cette semaine. Merci beaucoup. C'est vraiment admirable d'avoir ce sens du collectif, ce sens de l'entraide. J'espère que vous continuerez de l'avoir et que les autres le feront perdurer. Merci vraiment infiniment d'avoir fait ça.
Let's go.